A very good afternoon, ladies and gentlemen, and a very good morning to Dr. Hoffmann. My name is Raghavan Krishnamurthy, and I'm the Director of Steerix and authorized partner of RWTH International Academy, RWTH Aachen University, one of the top universities in Germany pioneering in Industry 4.0. Myself has been appointed as a Malaysia rep for this collaboration. So first of all, I would like to thank each and every one of you for your interest and participation. Today's webinar will be part 4 of our Industry 4.0 webinar series. And the topic is, why is machine learning an artificial neural network? And the next revolution in industry, how can you apply it? Okay, so before we start, allow me to give a brief introduction about Dr. Max Hoffmann. Dr. Max Hoffmann is the head of digitization and digitalization, manager at the Institute of Production Technology, IPT, which is part of the Fraunhofer Research Organization. For numerous years, he has been leading the Industrial Big Data Group at RWTH Aachen University and managed major projects with the German manufacturing industry. Dr. Hoffmann conducted projects on digital transformation with many large-scale German and international companies such as Volkswagen, Porsche, Saint-Gobain, and Bosch, to name a few. Today, he will be giving talk for 45 minutes and followed with 45 minutes of a Q&A. However, you can stop him halfway through during his presentation. Feel free to unmute yourself and ask him any questions, right? Otherwise, you can wait until the end of the session and ask him question during the Q&A, right? So without further ado, here's our speaker, Dr. Hoffmann. The screen is yours.
Yes, good morning to everybody. Good afternoon to you. Good morning to me. Here is 7:30, but nonetheless, I welcome you all very much to our today's session on. Today's session is actually deep learning, and what we will discuss is directly what comes after the discussion of last session, the data analytics. And today I will show you a little bit what further you can do with deep learning, which is a way more advanced technology than classical data analytics. So let me share my presentation with you to give you some insights here on how we can apply deep learning and artificial neural networks on today's problems. So please confirm you can share, you can see my screen?
Yes, we can.
Okay, perfect. Good, so thanks a lot, and let's start. So I just need to adjust something. By the way, if you feel like it, please feel free to also show your picture. It's always nicer to talk with human beings I can see, and besides talking to a wall of names, right? So I would really appreciate if some of you could also maybe unmute or show your video, that we can have a more vital interaction and a more vital discussion. Yeah, thanks a lot. Okay, deep learning, what it's about. Let me start with a few introductional words here. What technologies can we use, and how advanced is deep learning right now? You might deep learning, in fact, since a number of years, it became very steep attention curve. For example, if you see the Google Trends curve here, you can see that deep learning has gained majorly importance since 2012 up to now, and the interest is still rising. When you see the applications right now, which you see, then you mostly see in the news things like this. Computer playing Go against the best chess players in the world, also known as AlphaGo or AlphaZero. The big Google DeepMind engine behind this. You see engines that master chess like computers never before, and computer chess engines that had been trained for 20 or more years are beaten by DeepMind and AlphaZero chess computers in no time. But also, of course, for manufacturing optimization and energy optimization. And for example, Google, the founder of DeepMind, they also use it in their own data center. And they were able to reduce their cost of cooling their servers by amazing 40% just through the use of deep learning and artificial intelligence here, applied to their energy storage facilities and applied to their cooling system. But the question is, how can we profit from this in manufacturing and in robotics? So how can we adopt this trend around deep learning, and how can we make use of these deep learning methods and this advanced state in which deep learning is right now? So let me try to introduce to you how it even works, how deep learning works, how artificial neural networks work, without going too much into the scientific detail here. So characterizing deep learning, we can summarize that deep learning is in fact a part of machine learning, yeah, which we examined in the last session, data analytics. So deep learning is a very specialized and very advanced field of machine learning, which is basically the way of teaching computers to teach themselves. So in machine learning, we only give the computer a framework in which he's able to learn. And within this framework, the computer will be able to derive its own rules, to derive its own patterns, and to basically program itself. The deep learning is a very specialized field of this domain of machine learning. And the deep learning, the computer imitates the human brain by training their artificial neurons, by training their artificial brain, and by trying to evolve these rules in a human-like way. This is why in the deep learning sector, computers gain amazing results in learning very difficult things, learning things that we would have never imagined as a human, that computers or robots can learn this. The whole machine learning field, including the deep learning, is part of the bigger AI field, which is already around since the 50s. So where is deep learning used right now? Let me give you a few examples in which deep learning is applied already and in which deep learning is also needed. One is computer vision, analyzing automatically camera pictures, profiling, identification of humans, of objects, tracking, tracing, all these computer vision applications, and also, of course, used for autonomous driving and used for image classification. This is all based on deep learning. This very complex picture processing algorithms, they cannot be manually programmed by static programs with fixed rules. These applications, they have to use a human brain-like training method to be excellent in these kind of domains. Also, deep learning is a lot used in speech and audio. It means it's the analysis of a speech and voice recognition, and also, of course, voice to text. When we would like to automatically bring human voice to a textual form. And last but not least, the so-called natural language processing, which is not to be confused with speech and audio, because natural language processing means to understand written language, written text in their context. And this actually means that the computer understands the semantics behind a certain language, and understands the subtleness of certain languages and certain speech expressions and so on. And this is also a very, very big field, especially for recommendation engines, for sentiment analysis. For example, when we would like to automatically understand, let's say, tweets or posts, and all these applications, NLP comes to mind. This is already majorly used, for example, for automated stock trading. When we try to when we make computers teach to automatically understand news, and based on the news make very quick decisions to buy or sell something. For example, in this field, this is already majorly improved. Also in the, let's say, in the research of patents, this is already very used. You might know that if you want to bring a patent on the market, then it's very difficult, because there's probably thousands of pages you need to read in order to understand if there's even a market gap for your patent. But if you can use a computer which is able of natural language processing, you can automate the reading. So you can at least, for example, filter out a few documents which you need to read then. So all these fields, in all these fields, deep learning has brought a major improvement and has brought a major facilitation of manual tasks. So if we look a little further, what AI and especially deep learning is capable of is, of course, in predictive analytics. Yeah, we already saw this last time discussing about predictive maintenance, machine learning, text-to-speech, speech-to-text, image recognition, and then, of course, in the NLP section, classification, translation, data extractions, but also expert systems, planning optimization, and robotics. And in this session here, we will rather focus a little bit more on the robotics, because this is, I guess, a field which you can directly rely on, or which you can directly maybe implement in your business if you decide to use deep learning here. So let me quickly give you a short example how deep learning works based on a simple classification task. This is a simple image classification task, which for example, Google and all the other big providers understand now and are very, very well in. In this so-called supervised learning task here, it's the task of the computer to classify fruits. In order to bring the model to a certain state in which the computer is able to do that, the computer is fed with a lot of pictures, let's say millions of pictures. And additionally to these pictures, the computer will also get the labels of the fruits. Let's say he will see a couple of apples, couple of thousand apples, and he will also get this information that these pictures show apples. So then he can train towards these classes. He can train how this class of fruit, what it looks like. He will also get, of course, different fruits and so on. And then he will train his model in which he's able to predict a class or to bring a new picture into a class with a certain certainty. So here, for example, the pear on the top right, which is a picture that the computer has never seen before, the computer says, okay, I'm 94% sure that this is a pear based on the pictures which I've seen before of all fruits. And you see there, even the apple is classified as 62% being an apple. So these recommendation engines work really well right now. So how does this work in with neural networks? What does neural networks actually do in order to derive such a model, such a machine learning model? So what they do is they take the object, let's say the pear, and then there is some process involved, which is called feature extraction. This is very important. The feature extraction basically means when analyzing this picture, what features does the computer extract in order to do the classification? This might be the color, the shape, the length of the fruit, the different diameters and the different length parts of the fruits, and so on. All these features which are extracted from the pictures will be transverted into a mathematical object. It's basically the digital version of the real fruit, of the real thing. This feature vector has all the data in it which is needed to characterize this object. Of course, there must be some pre-processing involved. For example, we need to filter the background of the picture out in order to get the sole fruit first, and then we can do the feature extraction here to get the data in a mathematically representational form. Based on that, this feature vector will be fed into an artificial neural network. So you see a very simple form of neural network here, and you can use different algorithms to train this network. We have the k-nearest neighbor classifier, for example. We can use decision trees, support vector machines, and so on. And with all these different algorithms, we train the model in a way that similar features lead to similar classification of the classes. So the output of this neural network will be a so-called probability vector. So in this vector, there are all possibilities of all known fruits. Let's say the computer has been fed by 1 million pictures overall of 10 different fruits. Yeah, so every picture is represents one of the 10 fruits. Then this probability vector in the end will be 10 entries long. Yeah, and the entry with the most, let's say, likability will be the highest value. Yeah, for example, here it might be that the entry for the pear is 0.94, which is 94% certainty. Yeah, and the other 6% are distributed among the other 9 entries. And this way we can actually do the classification. Yeah, we train the model with a lot of data, and then when the model gets new data, it will classify the data with a specific certainty. So how does this neural networks actually work? Usually we have input layers, we have hidden layers in the middle, and output layers in the end. Yeah. Deep learning is actually called deep learning because we have these hidden layers. Yeah? We have these hidden layers which are quite characteristic for the human brain as well. And the presence of these hidden layers, which carry the activation functions of the single neurons, they make the learning to deep learning. Yeah, here, for example, we see a feed-forward network. This is an artificial neural network where the electrical signals between the neurons can only go forward, not backwards. So how is such a neural network configured now? Yeah. First, we determine the topology. That means how many neurons we have as an input, so how many features which we extracted go in. Then how is the processing core, the hidden layers, how they are configured, and what's the output. Between all these neurons here and between all these different levels in the neural network, which can have, of course, way more than one hidden layer. Yeah. So to activate all these neurons, we have so-called activation functions. This is basically the barrier of energy that a certain signal needs to have in order to pass through a certain neuron. Yeah, so, and when we actually define the topology, then the data will justify the weights between the neurons. Yeah, and this is the actual training process. So let's say the weights between the single neurons become thinner or thicker, and this way we actually train the neural networks, and the neural network is able to learn patterns. Neural networks are capable of doing all machine learning tasks which we know, for example, supervised learning, unsupervised learning, and reinforcement learning. So, for example, let's take a more complex example of a image classification algorithm here. Here on the left side, you can see that we insert pictures of faces. These faces are quite complex. There are different people, different nationalities. The pictures have different backgrounds. People have different hair color and so on. So it's a very complex picture. So what the neural networks does in the beginning is it uses some part of their brain to extract the patterns, basic patterns like lines or different color shades or something like this. Yeah. Then in the next hidden layer phases, the neural network is already able to detect some face features. Let's say the neural network will be able to see how does a nose look like, yeah, how does a mouth look like, how does eyes look like, and so on. And then in the end, the faces will be extracted, and the faces can be matched to known faces of the same person. This is, for example, how Facebook is able to directly show the names of the people in the picture, even though the algorithm has never seen this particular picture, but it knows the faces of the people quite well by extracting their features, yeah, the size of the nose or the distance between the eyes, the size of the forehead, and so on and so on. Yeah, so this way, mature algorithms are already able to characterize personal pictures quite well. Yeah, neural networks are very complex and can have many, many different forms and shapes, and many different ways the signal travels through. Yeah, I really don't want to give you any like deep technical details here, but just being said, there is a couple of uh, patterns which neural networks have. Yeah, there's, for example, the feed-forward neural networks, which you already seen before, and there is this recurrent neural networks where electrical signals are also able to travel back in the neural network. And there is, for example, these internal loops. And these internal loops you can see, for example, here in the middle of the left side, where we have the long short-term memory network. And these are actually neural networks where the electrical signal is able to travel back for a couple of neurons, and this way we can actually emulate a short-term memory into the neural network, because signals that repeatedly are driven back will be very strong in the beginning, but in the course of time, the signal strength will get low. And this actually is the same what happens into our human brains when we have a very fresh experience. It's very much on our mind, but if some time passes, this impression becomes less and less until we forget it. Yeah? Usually the short-term memory is just a couple of minutes, and this is perfectly imitated by such a long short-term memory network. Yeah, so we see through the different patterns, we can imitate different ways of human thinking, and we can imitate different ways of decision making in the human brain. So, but of course, for training artificial neural networks, we need a lot of data. Yeah, here's just some examples for image classification, for video classification, and for translation. So natural language processing. How much data do you actually need to train a functional model? And you see that you need many data points here. Yeah, for the image category data set, there was, for example, a 1.2 million images data set until the algorithm was functioning very well. We have thousands of categories, which gives us to 140 million specific features, which the neural network actually was fed with in order to be trained. Yeah, the same with the deep video. There we have about 100 million parameters to actually do an assignment of the video in one of the 47 categories of videos. Yeah? For example, for this website. And the English text, the translation of the English text was actually fed by the French text language body, and these were comprised of 380 million parameters, 6 million sentences, and so on. So you need a lot of data to actually make these neural networks functional. And yeah, this is basically what you also need to do when you, for example, train a robot. You need to train him a lot of iterations. Fortunately, this can also be done through simulations. Yeah, so you don't have to drive the robot million times. You can also do this partly in simulations to already do the big training in the beginning, and then you only do the fine tuning of the training in a later step where you actually use real robot data. Yeah, so one example of the advancements of neural networks is perfectly shown with video games. Yeah, here is an example of a computer trying to play the very old game Super Mario World. Yeah, it was in the beginning of the 90s. It came out on Super NES, and it was actually a game where you just run and jump. Yeah, so and the question now is, how can we make a computer learn this? Well, the fact is, if the computer plays this in the beginning, when the engine is not very trained, the computer is very dumb. The only thing he does is he runs forward, and then he will die very soon because one of the enemies will get him, and he has no understanding what's happening in the game. But what the algorithm does is this computer, which only sees the picture and only knows the action it can perform, which is left, right, top, up, and the 4 buttons, yeah, the computer will be punished with negative points when he dies, and he will get rewarded with bonus points when he lives longer. only through this punishment model, which is quite similar to the natural effect, for example, when we are a child and we learn how to walk, if we fall, it hurts. Yeah, this is a natural punishment. And this is why we learn how to walk without falling. And the same way is used by computers these days. Computers can actually play these games and learn based on the fact that they get punished if they don't survive. And if a computer plays this game actually millions of times, he gets very good. Yeah. So the neural network gets up in the so-called generations, which you see here. Yeah. And at some point, the fitness of the generation, the fitness of the player will be very high, and the computer will be very good to play this game. Yeah, and as you can see in the end now of the video, after these certain generations, the computer is able to play the game very well, nearly perfectly. Yeah, I think like we see it in the last frame here. At some point, the computer will learn how to jump, how to get over enemies, and so on, and be very good in the game. Yeah. But the important thing is here, and this is also one major critics about neural networks, we don't really understand how the computer learns this game, and the computer also has no idea that he's playing a video game. But he will be very good in it. So summarized, this deep learning can be used for different machine learning techniques. Yeah, we saw supervised learning, also, of course, for unsupervised learning, let's say dimensionality reduction, and of course, what we just seen, reinforcement learning, for example, for game AIs, real-time decision making, and also for robot navigation. Yeah, this can give us many advantages in different manufacturing sectors. Yeah, for flexibilizing our manufacturing systems, for getting more efficient production systems, and also in the business area, for example, for prediction of global sales and knowledge transfer. Yeah, I don't want to stress on this too much because we already examined this last time. But of course, neural networks can also optimize these areas here. And again, this leads to shorter delivery times, more robust production to robots, better usage of working hours, reducing human errors by making computers automatically train the optimal process, automation of human activities, which is very redundant or very difficult to perform. We can have safer working conditions, for example, by image classification, yeah, to understand dangerous situations. We have, of course, lower overhead costs in the end, and will gain new variants of the human role. So let me give you one example of self-learning robots by bringing a project which I once did, where we trained a robot to teach himself. This is real applications of deep neural networks in the manufacturing sector, and this could be also an example where you could start out with today. So what we're trying to teach the robot was to perform a certain movement. And this movement is characterized by the game, you might know it, it's called the hot wire. And the goal of this game is that you follow the complex shape of this wire with a ring without touching the wire. Yeah, so always if the ring touches the wire, becomes an electrical signal, and you have to start from the beginning. So it's kind of hard to teach a robot such a curve to perform such a movement. And in the classical robot domain, of course, you would have to train the robot. Yeah, you would have to teach him every single move. You would teach him every single centimeter that he has to do, and every rotation and every forward and backward, to just imitate the wire perfectly. And if the wire changes, if the wire has a different shape, the robot needs to learn all over again. So we, of course, in deep learning had the goal that the robot learns how to play the game, so the robot in the end can play any artificial wire that the robot actually wants to play, or that the robot gets. So how is this done? This is exactly done in the same fashion as the Super Mario example was trained. Yeah, and the basic model is the so-called agent environment model. And in this case here, our agent is a computer that controls the robot. So the agent performs action. And these actions are moving forward, rotating, getting faster, slower, and so on. These actions which the agent performs will be executed in the robot, and this will have an immediate effect on the environment. And the environment will then react with a new state because we change something in the environment, the state will change. And most importantly, the so-called reward function. And the reward is the bonus if you, let's say, don't touch the wire, and the penalty induced by the electric shock when you touch the wire. By training the robot how to play this game based on this reward punishment model, the robot will learn intuitively what he needs to do in order to not touch the wire. Yeah, so and then the weights of the artificial neural network here will be trained accordingly, and the robot will know in each situation what to do. How to do that? First of all, we need a model. We need a model which is able to describe the situation in a mathematical, computer-like way. So here is a very abstract picture we took from the wire using an infrared camera. So this infrared camera can basically see what is the background and what is the wire. So it can extract the features of the wire and can get the basic shape. Of course, some pre-processing also has to be involved here, like in every machine learning project, in order to bring down the calculation times. We did a little downscaling of the image. Yeah, so we brought the image down from 1152 times 720 pixels with infrared camera to 25 times 15 pixels. Yeah, which is of course a way lower resolution, but it's still enough to characterize the position of the wire quite well. So after this downscaling, of course, we also have to design a representation of the robot, of the ring. And you can see this in the bottom left of this picture here, where we actually see this blue box, yeah, with the ring on the top and the bottom, which represents actually a picture of the ring which is surrounding the wire. Yeah, so the environmental state we can then bring down to this very small 5 times 5 pixel picture, which is next to the wire picture. Yeah, where you see the ring in blue, the current wire in red, and the next wire part in green. So this environmental state then can be formalized by a feature vector. This feature vector, which is called here x1 to xn, this can be used as an input of a neural network. Yeah, based on this input, based on the feature extraction, which is done based on the small 5 times 5 pixel picture, the neural network is actually able to learn and to evaluate the situation. So the model can decide when the features have been traveled through the neural networks, the computer can decide what the robot needs to do next. Go up, go down, go left, go right, and rotate. Yeah, this algorithm here, which is used, is Q-learning. Yeah, this is actually performed by an initialization first, then the robot chooses an action, and then the action will be performed, and then the reward will be measured. So the reward measurement is actually simple here. Touching the wire is a positive reward. Non-touching the wire is a positive reward. Touching the wire is a negative reward, so a penalty. Yeah, and then the Q model will be updated. Yeah, and based on this Q model, the weights, these are the connections between the neurons, will be adjusted. And based on that, the neural network will get trained. So in the end, the robot basically needs to do in every single situation which action to perform. And the algorithm should see the world, or should see the actual situation in a similar way to the human being. Yeah. So how is the hot wire game played now? Let me summarize this again in 4 steps. First, we have the sensory acquisition of the wire with the camera. Then we do the image processing. We scale down the image. We extract the relevant part of the image. And we can bring this all down to the current world model, how the robot understands its situation. Then the robot learns an optimal strategy, yeah, to reach to the end of the wire without touching it. And for this, he needs to make the perfect movement in every situation. And what we want to do then in the end is we want to transfer the learned technology to a general movement execution of the robot. That means we want to transfer the knowledge that he gained to any arbitrary wire, because we do not only want to train the robot for a specific wire, we would like to train him to play any possible wire pass which he will get. Yeah? So summarized here on this picture how this all works. Yeah, we have a camera which is actually on top of the robot head, let's say, yeah, and this camera gets a picture. This picture will be transferred into the environmental model. This will give us an environmental state, and the feature vector which is extracted from this environmental state will be put into the neural network. Then the neural network, the artificial brain, will process this input vector and will derive actions. Yeah, here actually they're shown in German, but they mean up, down, left, right, forward, backwards, and rotation in both directions. This actions then can be fed to a REST API, which directly controls the robot movements. And based on this model here, the robot is able to play the game. And the same as in Super Mario, the robot will learn in generations. That means in the beginning he's very bad, in the end he will be very good. Yeah. Here I brought you a few examples of how such generational learning in computers can take place. Here's, for example, an engine which learn how to actually control artificial muscles in different creatures. Yeah, here's the human. Afterwards, we will also see different animals. Yeah, as you see in the beginning. Let me fix that. In the beginning, the generations are very bad, so the movements are not very accurate, and the creatures fall down. Here, for example, for a giraffe, yeah, giraffe is a very complex structure that even after many generations, it doesn't know how to work perfectly. But in the end, after a high number of generations, the model will be trained very well, and all the different muscle tractions and all the movements will be optimized very, very precisely. This is how basically a neural network gets better in its different generations. Yeah, and from a more technical perspective, this somewhat looks like this. In the beginning, we have the same weight between each neurons. Yeah, and then when the model gets trained with data, the connections between these neurons get thinner or thicker. And this is actually the training process. So the electrical signal will distribute itself according to the thickness of the lines between these neurons. And in the end, we have a trained state in which basically in every neuron, the next action is determined. Yeah? And so in the end of the neural network, we will get the results, which is combined of all the different electrical signals traveling through the neural network in different paths and in different directions. So how does the robot actually do this? Let me show you here in practice how this was performed. So on the top left here, you see the current state view of the robot. In the bottom, you see a simulation of the robot and the wire. And you can see how the simulation affects the current state of the robot if I run this video here. Yeah? Let me fix that. Yeah, so we actually see that the robot recognizes the different angles of the wire, and then accordingly changes their direction, changes their movement, and changes their angle. Yeah, and this is actually how this whole system was trained for, and how this whole system works. Yeah, and I also have a real video of the actual experiment that we performed, yeah, which was basically demonstrated also in the Hannover Fair 2018, which is the biggest industrial fair in the world. Yeah, some people from big companies of you might know it. It's the biggest industrial fair actually that we have. And yeah, let me show you how the robot movement actually performed there. So here we see the real robot and the wire. And we see basically the robot having these two steel needles, and the robot needs to run along these tasks without touching the wire. You see the infrared camera, which is basically on the forehead of the robot. And in the first training, of course, the robot is very slow. Yeah? He would just touch the wire. He would just make a movement forward, and he would just touch the wire, and he will not be able to adjust very good. Yeah, so he will make wrong movements, touch the wire, get penalties, and so on. After 30 minutes of training, and this can also done by simulations, by the way, the robot was already able to play the wire quite well. But the robot was only able to play this one wire very well. Yeah. So if we would, let's say, change the wire in the course of the experiment, the robot would have troubles. Yeah. But after half an hour, this one wire was played sort of perfectly by the robot. Yeah, as you can see, it's still a little itchy. Here's again the physical representation of the robot, what the robot sees, the picture, the infrared picture, and the virtual world representation. And yeah, so the robot can play the wire. Now, when he's done with this wire, we will actually see how the robot can perform after 2 hours of training. Yeah, after which the robot was trained to play any artificial wire. Yeah, so after 2 hours of training with different wires, we can actually change the wire live, and the agent will learn the wire within a few minutes. So he will be able to play the wire perfectly, even though he has never seen the wire before. And this is actually a major advantage compared to current robot automation, which we have. Because this spontaneous learning of a new movement, yeah, there is no programmed robot which can do that. Yeah, there's no trained robot which can do that. This can only be done by robots which have artificial neural network, yeah, which have basically an artificial brain which is able to understand and perceive the current situation. Yeah, and here we even can adjust the wire in live while the robot is playing, and the robot will still be able to do it. Yeah, and this is very amazing. Yeah, and this is yeah, really good. So this was a project which we did at the RWTH Aachen University, and which was basically a showcase for the industries, what they can do with deep learning, yeah, and what they can actually perform. So with this last sentence, I would like to thank you very much for your attention. And now we're open for questions.
Thank you, Dr. Hoffmann. So ladies and gentlemen, it's time for Q&A. So please feel free to unmute yourself to ask question directly to Dr. Hoffmann. Any questions? Right. So meanwhile, waiting for questions from the floor. Dr. Hoffmann, from real practical industrial point of view, how or when can we start applying this deep learning? So is there any requirement prior to this? So is there any advice on this?
Yeah, so basically, for example, to realize such a project that we've seen just in the end now, the only thing we need is a programmable robot, which can also be remote controlled. Yeah, so we need to have some API or some interface to the robot, which we can use to feed movements or feed commands into the robot, which will then perform. All the software And all the training which we use for the image processing, for the feature extractions, for the training is all based on open source software. We don't even need a very expensive camera. We can use a simple infrared camera for maybe very light situations. For other situations where the background doesn't change, we even might be able to do it with a normal webcam. Yeah, and all the software which we need there is actually open source. Yeah, this is, for example, also the software which we use when we do the class in big data analytics. Yeah, all this software is based on Python libraries, and we can apply deep learning techniques to make the robot basically learn all these things here. And yeah, so the barrier actually to start out is not that high from an investment point of view. Yeah, it's just that you need the skill set to use these open source libraries to perform such a model training. But this can be taught, in my opinion, in 1 to 2 weeks.
Okay, thank you. And we still don't have questions from the floor. If you guys feel uncomfortable to unmute yourself, you can also raise your question in the chat box. We will ask the question on your behalf.
Hello, this is Andy here. Basically, is this model can be done without any data beforehand? That means I start with raw, no data at all, then I directly jump into this field?
Yes.
Or do I need to actually prepare some basic data then to fit in first?
Yeah, so the answer to this question is actually not quite simple, because you basically can start out without any data. Yes, you can train from the very beginning without any prior knowledge or without any prior data. But then the training, of course, becomes very lengthy and very complex. What you usually do is you do a training where you already have a predefined data set, or you have a predefined simulation, or you even have a predefined neural network, which is already optimized for movements. And then based on that, you make the model perfect by training with new data. But from a general perspective, if you would say, for example, train a robot movement to perform like we just seen in the video, we need no data in advance. Yeah, we only need to let the robot play. We need to make sure that all the data flows are in place, yeah, that we extract the picture properly, that we process the picture properly, and then we can basically start with zero. Yeah, it will take some time, of course, and it will be way faster if we're able to set up some simulation and to generate some artificial data, but it can be done without any data.
So if I change the length of the wire, so this one also will be able to train, right?
Yes. So
I mean, not the length, the width of the wire.
Yes, what we have seen in the video. So we actually had 2 stages of the project. In the first stage of the project, we had a camera which sees the entire scene. Yeah, which sees the complete wire from the beginning to the end. Then it would have been difficult actually to change the length of the wire. But in an advanced stage of the project, we, as you have seen it in the video, we attached the camera on the robot itself. So the robot will only see where he is right now and the next few centimeters. Yeah, and of course, if the robot only sees its current position and the next few centimeters, the wire can be as long as it wants. It can be kilometers long, yeah, because the robot will only evaluate its current situation and the next couple of, let's say, centimeters. So yes, the wire can be here any arbitrary length.
So when I got different width, that diameter wire, actually I need to retrain the model again, no?
So that's what I explained. in the beginning, where the model training was not very advanced, we had to retrain the robot for every new wire. But actually, after 2 hours, the robot was trained to play any wire directly. So after we trained the robot with our advanced algorithm for 2 hours, the robot was able to play any wire directly. So there was no additional training needed. We even, as you've seen in the end of the video, we were even able to change the wire while he was playing, and he was still not touching it. So actually, no, we don't have to retrain the model when the wire changes. This is actually the goal of the deep learning model, that the training we provide for the robot gives him such a general understanding of the situation and of the scenery that the robot would be act perfectly in any situation here without further training.
Okay, thank you.
Sure, thank you.
Thank you, KY.
Hi, this is Azidi from Inari. I have a question to Dr. Hoffman. In the perspective of the high volume manufacturing, especially in the semiconductor high volume manufacturing environment, where do you suggest the usage of the deep learning type of robotic system compared to the existing industrial robots? Do you have any suggestion in terms of example of the area that we can be used,
Yes.
Can be used? Okay.
Yeah, that's a very good question. Thank you. Actually, I know semiconductor field quite well because we already did some trainings for some semiconductor providers, also Inari. Yeah. Just Ragavan, help me here. Which big company did we do the training for in IPO?
Finisa.
Yeah, Finisa. So we did a lot of training with big companies, and we know the semiconductor field quite well. And I also seen a couple of factories. And when I was walking through the factory there, I had many ideas what to do. And the first thing which comes directly in mind, especially with the high quality standards in the semiconductor field, is actually to use deep learning for quality control, quality inspection, and in this field especially image processing. Yeah, when I seen the working environments in these factories, for example, I saw a lot of manual inspection tasks, which is of course very high quality, yeah, because every chip, let's say, will be inspected by an expert and will be evaluated. But the human eye, especially if the worker does basically the same all day, doesn't work perfectly, and some errors might be involved in the end, yeah, and this might lead to products which cannot be shipped out, or to reclamations, or whatever. So what I would actually suggest as a major starting point in semiconductor field was revolutionizing the quality control by automatic image processing. Yeah, if we look at the automatic automatic microscopic pictures of the chips, if we can directly with computer vision can make a pre-classification, and maybe only 10% then needs to be inspected by a human, then we would already have a tremendous boost in OEE here, my opinion. Did you target this field, or do you mean maybe more the manufacturing part itself?
Yeah, basically, because right now manufacturing, sometimes we are going for the standard products, and in terms of teaching the robots or even teaching the vision system is already there. There's several libraries are already there. However, I'm more interested in the so-called deep learning, such that we are talking about sometimes non-standard products are being used. How can we shorten the learning curve of any processes or even the inspection system, such that the new product being introduced will not take too long of a time for development in the manufacturing.
Yeah, so actually in this case there, if I understand you correctly, you would also like to optimize special products with small lot sizes, right? Where you don't have millions of products where you can learn on. Yeah, this is actually a specialized field of deep learning, which is called transfer learning. And in this field, you try to transfer the knowledge about patterns which you gained from another, let's say, product, let's say another microchip, and apply it to a new model. So what basically we would need to train here is a deep learning algorithm, which is able to learn how the general surface of a microchip, for example, looks like, how the wires look like, how the other surface components looks like, how condensators look like, and so on. Yeah, so the model basically needs to learn the basic patterns which are present on every microchip, but however in different order and different size and in different shapes. Yeah, but if we could actually train the deep learning model all these different features, for example, what a wire on the chip looks like, yeah, and so on, and what a conductor looks like, then all these patterns we can actually apply on a new model. And then in the end, if we have a new specialized product, we only need to give the robot basically the coordinates of each little components on the microchip, and based on this this wired image, yeah, based on this let's say product specification, the robot can maybe directly understand the new chip, the new product, and after a few products of training, he will be able to also inspect this one. So this is done by transfer learning.
Thank you. And one last question is that if you're currently having a vision system for inspection, how, or rather, my question is that, is there a open source system or open source software that you can, you know, download it in such that
Yes.
similar? Go ahead. I think you know what my question is.
Yeah. So the yes. Thank you. The basic library, which we also use in our trainings, is the so-called Keras library based on Python. Deep learning. Yeah, this is a deep learning library. It's called Keras and is based on the scikit-learn library from Python. And you can download this and you can use it directly to train artificial neural networks. It's completely free of charge, of course, because it's all open source and you can directly start out. Actually, in one of our trainings, which is called Big Data and Analytics for Cyber-Physical Production Systems, we exactly do this. Yeah, we teach the basic machine learning methods, how to deal with the programming language of Python, how to use the machine learning libraries, and then in the end, we also look at how to train artificial neural networks with Keras library. And it's a very simple configuration here. You add the input layer, you define the features, you add some hidden layers, you play a little bit with the parameters, you define the output neurons, then you train it with data, do some model evaluation, and based on this evaluation, you can adjust your parameters. Yeah, let's say the number of neurons, number of layers, and so on. And it's a very iterative process, which doesn't even involve so much coding. Yeah, so you don't have to think that only like full-time programmers can do this kind of things. Yeah, actually, these new libraries, especially open source libraries, have gained tremendously in simplicity in terms of implementation. So I think a smart engineer can learn this in 1 to 2 weeks, how to apply such a library and how to feed such a library with the according data.
Thank you very much for the answer, and Dr. Hoffmann. Thank you.
Thank you for the question.
Thanks, Engineer RCD. Any other questions? So we don't have any question yet. No question in the chat box as well. Okay.
Hello. Okay.
Hello.
It's me again. I want to ask, is there, because I'm still new to this field, right? So is there a way to make such deep learning able system from scratch? Because right now it's like I'm blank, I don't have data, don't have model, don't have anything. Then I want to do something. Then with like everything is blank. So just say, okay, just say if I got the software knowledge, then I think, oh, maybe I can design the system. But it will be a bit inefficient, right? To go through everything again, right? So any advice from here?
Yes. Yeah, of course. So if you completely blank from the data set, let's say, then you actually need to perform a few steps before, of course. Yeah, as we already mentioned in the very first session of this webinar series, the first thing you need to try to reach is this so-called Industry 4.0 maturity. And this, of course, starts with looking what sort of data sources you have, what sort of data sources you can use. So this is the first thing you need to do. You need to say, okay, we don't have any data yet, but I would like to be clear about which data I can get and which data I can collect. And when you have this, then you can actually start collecting your data. And then you can examine, okay, what kind of robots do I have? What kind of interfaces do I have? Am I able to control them remotely? And when you're clear about this, so when you have a database in which database data can be stored, and when you have the robots which can automatically be controlled, then you need to find a smart way of how to record the data. And this can be, of course, done by image processing, but this can also be, of course, done by a parsing of the raw data from the robot. And then we will store the coding data in the database, and then we can basically start with the training. And yeah, in order to start out with this, of course, you need a training. Yeah? So you need to know how to perform all these steps in a structured way and how to start out with the machine learning programming. But again, I mean, I already mentioned this. We have two structured classes. The first class is the machine-to-machine communication seminar and cyber-physical systems seminar, where we focus on these very basics. How do we get machine data? How do we store machine data in a structured way? How do we set up our environment, basically our data and database ecosystem? Yeah, and then our second seminar is actually on AI, deep learning, and machine learning. And there we look at how we can use this data, how we can, what kind of operations can be performed based on this data in order to apply machine learning. Yeah, this is a very structured approach, which is of course complex. Yeah, the industry is a complex field, and the solutions we can apply here are not easy. Yeah, that's why you actually need this basic knowledge. But as I said before, I'm sure this basic understanding and this basic ability to start out can be gained in 2 weeks.
Okay. Thank you.
Sure. Yeah, so everyone, feel free to ask questions. Yeah, also about general industry 4.0 topics, of course, which are touched by this deep learning field here. Yeah, so also if you have general questions about machine-to-machine communication or industry 4.0, feel free to ask them here.
Any questions? We have another almost 30 minutes. Okay, I would say about 20 minutes. So please take this opportunity to ask questions, Dr. Hoffmann. Yeah, as he mentioned, you can also ask anything from the previous section, right? From the previous session, anything regarding mission to machine or, data analytics, right?
Can this be integrated with other language, like example .NET or Java, some kind of application development?
Yes, so this can be integrated in a few ways with other languages. Yeah, usually also if we have information architectures, they are usually designed in a multi-language pattern form. Yeah, so let's say we have a service-oriented architecture in which services are able to talk with each other. Then it's actually in most cases we have different programming languages here in charge. Yeah. The only thing we need to define is the interfaces between the systems. So we can have, for example, the robot automation and the data aggregation we have implemented in, let's say, .NET or C#, and then the learning we can implement in Python. Yeah, this is really no obstacle today anymore, because the interfaces are quite interoperable at these times, and we have generic data representation and generic data structures to do this. The second way, besides this service-oriented architecture approach, is actually to use wrappers. So right now, it's also easy to actually have, let's say, .NET wrappers in Python or Python wrappers in .NET. So these are two ways we can do this, and the presence of a certain programming language as a prior implementation language doesn't mean that we cannot use any open source libraries based on Python. In my opinion, they are usually interoperable.
Okay. So do we need to install some kind of application within, example, if I have a Visual Studio, so do I need to install some add-on something like that for this?
Yeah, of course. I mean, Visual Studio is an programming environment for .NET applications. Yeah. Of course, when you would like to program in Python, then you need to install a Python interpreter, a Python 3 interpreter, or you can install already a pre-configured Python interpreter with many important libraries present. For example, the Anaconda package, yeah, which we also use in our seminars. And if you have this installed, you can basically program in any IDE, yeah, for example, Visual Studio Code, or in some specialized Python IDEs, or you can also use interactive Python notebooks, which we also use in the trainings. So this is actually everything you need, yeah. In the same fashion you install .NET, you install Python.
Okay. Okay.
Okay, thank you. Sorry, I couldn't address you because I can't see your name.
My name is Raghunath.
Okay, thank you, Mr. Raghunath. Okay, we don't have any question from the chat box yet.
I have one question about standards.
Yes.
Okay, today in our industry, when we want to start on these projects, there are many potential projects in many diverse areas. It could be in QA, quality assurance. We want to check the quality. We want to look at defects, or maybe it could be in the area of ERP. We want to look at the trends of scrap and all this. It could also be in production. So there are many potential projects. So let's say if we start embarking on one and then we start doing it, then later we see that this successful, and then to start the second one and the third one. So is there any any way or whatever they can do that we set a standard or framework so that later when we have multiple projects, it makes it easier to do the development. We don't have to like start all over again. How to approach this, having a framework or standards?
Yeah, of course. This highly depends on the domain, right? So we have to actually look in order to use such kind of standards. We need to precisely look what sort of data we are usually using within our domain. And by doing this, we can actually implement some blueprints. So some blueprints which are already shaped in a way that we can target them with new problems in our domain. I'm not aware of existing official standards for deep learning implementation. And this is due to the fact that the field and the diversity of data that we have there is too high in order to give some fixed guidelines, for example, how to program a robot. Yeah. The basic thing is basically you have to start building up a knowledge base in your company, and you need to find ways of standardizing this. In the machine-to-machine sector, we have already a big standardization. But in the deep learning sector and in the artificial neural network sector, this field is, I would say, too new to be officially standardized by commissions, because these commissions are usually also not so much on the, let's say, on the pulse of the current times to define such standard in a meaningful way. You can certainly define such standards, but they might work for one or two of the users, but not for all of the others. You basically need to try to set up your company ecosystem. Like one example, what we also do in the training there in this direction is we talk a lot about so-called big data ecosystems. And there is a big picture which is called the big data landscape. And you see many libraries and programs which you can actually use for every single application domain. And what you need to do as a company in the beginning is to take a strategic decision towards how much in-house knowledge am I willing to build up, and how much knowledge if I am willing to buy in. If the strategic decision of your company is, I would like to invest in my in-house knowledge, then you can build such a framework. Because then you will be able to actually understand the similarities between your processes. If you buy in more solutions from suppliers, then of course you can shape your ecosystem and your framework based on the solutions that you get from these. But then of course you have to basically stick with the same distributor and be sort of in a dependence, let's say on Microsoft Azure or something like this, or on Amazon Web Services or some other very specialized providers. So my advice is the generation of a company internal framework, I think, is very vital and will be very important, especially in the next 5 to 10 years. And in order to build such a framework, you need to build this in-house knowledge, right? And you need to build up here on your competencies.
Thank you.
Sure, thank you.
Thank you, Mr. Lee. Okay, we have a question or request. I would say, could you please share or give the name and the link for Visual Inspection Software Python library? Okay.
I mean, there are many libraries. Basically, there are, if you just Google for Python deep learning image classification, you will probably will come to the Keras library, and there's also one library which is used for image classification. I can just look it up very quickly what it actually. Just give me 1 second. Yeah, I can even tell you right now what the library for image processing is called. Yeah, it's called OpenCV. Yeah, this is a very well-known library, and OpenCV can also be integrated with deep learning. And the OpenCV library is actually the state-of-the-art library for image classification.
Okay, so thank you. Right, so Dr. Hoffmann, so just a question from my side here. So earlier you mentioned you still can start this deep learning without data. For example, the hot wire thing that the robot was playing, right? So, but it comes to things like image processing, whereby you do some visual inspection, you need to have some basic images, because from your slide earlier, it shows that for image processing, that's one situation, one application that requires almost 1 million of images, right? So what will be the minimum images or cases, images that if we look at a manufacturing environment, they're doing a lot of visual inspection, as you said. So what are the minimum number of images or data that we should have before we start working, and how long will it take? Because how much data we need, and if we want to take the lengthy training process, it may not be feasible at a production. Yeah. So how much data would we need, and how do we get this expedite and all that? Could you advise on that?
Yeah, I think in 2015 we would have needed 1 million pictures. In 2020 we maybe need 1,000. So we can actually be glad that we live in 2020 from this perspective, because now we have this pre-trained models, so-called pre-trained models. And this is exactly what I meant earlier when I was talking about transfer learning. Transfer learning means that we already have models that understand basic patterns and shapes. So what I showed in the beginning was first in the face recognition, the basic shapes are and the basic curves are extracted. And then we can actually come to a nose or a mouth or something like this. Yeah? And also in image processing for specific domains, we have so-called pre-trained models right now. So there might be even, I'm not completely aware of this, but there might be even a pre-trained model for chip inspection in semiconductor industry. So this model has already been fed by millions of semiconductor pictures. And in order to optimize the model on your specific product, you only need a couple of pictures, yeah, a couple of 100 pictures maybe.
Right, thank you. That is a good news, I would say, because now rest assured that a company can immediately look into this visual inspection and deep learning for their daily process, right? Okay, so
Exactly.
And there's no more question from the chat box. And is there any question from the floor? So maybe we can take one more last question if there is any question. Otherwise, we can wrap it up. No questions? All right, I think we have come to an end of this part 4 of our webinar series. So ladies and gentlemen, this talk is brought to you by Steerix in collaboration and supported by MPC, EEPN, and MGCC. So stay tuned for our next part 5. We will communicate to you on the details of registration and the link for the webinar. And meanwhile, if you have any questions or you want to contact us, please feel free to contact us or email us at info@steerix.net. All right. Thank you, Dr. Hoffmann. Thank you, everyone.
Thank you. Goodbye.